So hi everyone, my name's Emily Nightingale. I'm a postdoc at the London School of Hygiene and Tropical Medicine. And I'm afraid my link to the theme of this session is somewhat tenuous. And I'm sorry to disappoint everyone, but I'm not going to be mentioning vaccination at all. But I will be talking about the interpretation of routine surveillance data for a disease near to elimination. So poliovirus, which is a vaccine-preventable disease. So there's the link. But yeah, I'm going to be describing some work that we did with the polio eradication initiative to do with estimating the sensitivity of routine surveillance and the information that gives us about declaring elimination. So in any sort of near elimination scenario, regardless of how the surveillance system works, it's going to be yielding an increasing proportion of negatives as we sort of reach that end goal of elimination. But the problem is that we know that surveillance is not perfect, and importantly can be quite variable in terms of its sensitivity and its performance over time and between different geographic areas, so between administrative units at which these data are interpreted. And that makes the interpretation of those negatives quite a challenge. So we want to understand how confident we can be that infection is indeed absent, given that our surveillance system is only returning negative results. Now, if we think of the entire surveillance system as a single result from a complex population-level diagnostic test, then we can interpret this sort of question in terms of the negative predictive value of that diagnostic test of the surveillance system. So this is the conditional probability that infection is absent, given that we've observed a negative result. And in the context of this project, we've defined that as the probability of freedom from infection on a national level. So to infer this negative predictive value, we can infer this if we understand the sensitivity of the surveillance system for detecting infection. So that's a conditional probability in kind of the other direction of a positive outcome if the disease was indeed present in the population at a certain level of prevalence. And in the case of polio, we've got a sort of multi-component surveillance system consisting of both case-based or clinical surveillance and environmental surveillance, both of which have their own sort of strengths and limitations in terms of detecting infection. And indicators of the performance of these two surveillance components are routinely collected and monitored, which indicates heterogeneity in performance, as I said, over space and over time. But this monitoring of performance is interpreted in parallel to the resulting sort of positive or negative observations, rather than directly integrated into their interpretation. So knowing that this heterogeneity exists, we clearly can't interpret the positives and negatives observed in different places and at different points in time as conveying the same amount of information about underlying presence of infection. So what we want to do is to incorporate this information about variability performance into our interpretation of the negatives that we've observed in this near elimination setting. And to do that, we've extended an approach which was actually developed out of veterinary applications, so applications of inferring confidence that a herd of animals is free from infection prior to transportation or trade. So we use this approach which models the sensitivity of the surveillance system via scenario trees. And from this, we can quantify the accumulating evidence of freedom from infection, or the accumulating negative predictive value of the surveillance system on a national level, given that variable strength of surveillance across districts and over points in time. So as I said, there's two key components to polio surveillance in endemic areas. So first, case-based, so the testing of stool samples from notified cases of acute flaccid paralysis among under 15-year-olds. And this, by design, can only detect symptomatic infection. So you're testing a population who are already presenting with clinical symptoms. So that is a sort of limitation in terms of its representativeness of infection. But it is something that's implemented nationally. So regardless of where in the country the case is notified, it still sort of triggers the same surveillance response. So in theory, everyone who is covered by the primary care system should be covered by this surveillance system. On the other hand, we have environmental surveillance, so the sampling and testing of wastewater from rivers, open drains, canals, different waterways, which can obviously detect the presence of either symptomatic or asymptomatic infection, but within the catchment of that particular sampling site. So it's limited in its population level coverage because it's only conducted in certain discrete locations. So ultimately, these sort of characteristics create a pair of surveillance components which are kind of complementary, but there are still gaps even when you combine them. So in order to understand and kind of quantify the overall surveillance sensitivity, considering these two independent sort of components, we define, as I said before, what we refer to as a scenario tree, which captures the sort of individual steps through which an individual infection needs to pass in order to yield a positive outcome from that surveillance component. And we consider the pathway of a single individual and the probability of them passing through each of these steps and yielding a positive result. And what so this is our sort of like relatively simplistic model of the surveillance system. And we want to define with some level of uncertainty the sort of stepwise probabilities of passing through each of these individual stages. Now, for some of these components, we consider them to be likely very relatively constant over space and over time. So, for example, the development of clinical disease for wild poliovirus is around 1 in 200 infections. So for these components, we specify a fixed distribution based on sort of understanding from the literature. Oh, no, there we go. But for other of these, we do consider that they're going to be variable between over space and over time. And so we take advantage of those routinely monitored indicators of surveillance performance to inform a probability distribution based on recently observed data in each particular geographic unit that's updated for each time step on a sort of rolling basis to give us a sort of a local and a time-dependent measure of the probability of progressing through each stage based on data from that particular area. And aggregating across all these steps gives us an overall probability that an infection in a particular district would yield a positive outcome either via AFP surveillance or environmental surveillance. Now, also on a sort of subnational level, there's going to be a differential risk that infection is present overall. So we sort of construct a measure of this differential risk based on population size, estimated immunity in that particular area, previous positive detections, and a simple radiation model of risk to neighboring districts. So combining this differential risk with our sort of individual level probabilities of passing through the surveillance system, we can estimate a measure of surveillance sensitivity across the country as a whole. So the probability that the entire surveillance system across the country would yield a positive observation, given that infection was present in any district. Now, when we talk about sort of presence, absence of infection, what I really mean is presence at a certain prevalence that could sustain transmission. So this is a context where we're thinking about the declaration of elimination. And so we want to understand from our surveillance system the evidence that infection is at least below a level that would result in the interruption of transmission. And we call this the design prevalence. So the prevalence of infection that the surveillance system is designed to detect. And as I said, we want this to be low enough that that transmission could feasibly have been interrupted. And in this case, we define a threshold of 1 infection per 100,000 population on the subnational level, which is consistent with what some other studies have used, but is still sort of subject to debate, and we've done some sensitivity analyses to kind of explore the impact of this. But that sort of 100,000 is our critical threshold level that we're sort of focusing on to understand the sensitivity surveillance. So to kind of explore whether this approach yields some sort of sensible conclusions, we used a retrospective example of the elimination of wild poliovirus type 1 in Nigeria. So here we have an interesting case where between the years of I just realized it's not actually gone. There we go. Between the years of 2014 and 2016, there was a complete absence of detected infection, so either through AFP surveillance or environmental surveillance, despite the fact that there were 27,000 notified AFP cases during this period and over 1,000 environmental samples. There were no positive results. So we wanted to look back at the surveillance performance data and the amount of activity that was going on with respect to these two surveillance components during this period to understand what kind of level of confidence in underlying elimination would have been achieved during this period of 2 years, how much would have accumulated, how much evidence would have accumulated. So in this case, elimination was almost declared by 2016, but in fact, there we go. 4 more cases of clinical wild poliovirus were then detected in the middle of 2016 in the northeastern state of Borno. So in this scenario, we kind of retrospectively know that elimination was not achieved and virus persisted, the sort of transmission of the virus persisted. So we want to see how, what level of confidence our approach would have concluded in that time. So in the interest of time, I'm going to sort of skim through the next couple of slides, but this is just to illustrate the sort of type of, the extent of heterogeneity that we observe in these like indicators of surveillance performance during this period of time for Nigeria. So between local government authorities on the right-hand side, and these are the same, but just over time on the left. So at the top, we've got the overall notification rate of AFP cases, which according to the WHO sort of targets for sufficiently sensitive surveillance should be above 2 per 100,000. And on the bottom, the proportion of those notified cases who have adequate stool sample collected for analysis. And then sort of comparably for environmental surveillance, we've got a few different metrics of performance. So the number of, the sort of frequency of sampling, the overall population coverage that's captured within the sites that are collecting samples, and the rate of detection of non-polio enteroviruses among those samples. So these all indicate all indicators of the sensitivity of the environmental surveillance that's going on. And so we feed those data sources into our stepwise probabilities within our scenario tree to estimate on a national level the sensitivity of these two surveillance components for detecting infection if it were prevalent in the population at that 1 per 100,000 population prevalence. And then using sort of standard rules of probability, we can take those estimates of sensitivity and translate them into the negative predicted value or the probability of freedom from infection on a national level. And look using Bayes' rule, sort of updating each of these sort of probabilities over time at the accumulation of confidence in absence of infection for each additional month of that we're observing negative results. So this is from the time period of 2014 to mid-2016, when for every month the system was only returning negatives. And we can see that by the time that that wild poliovirus was sort of detected in Borno state, our approach is estimating a probability of free infection between sort of 80 and 90%, which sort of out of context maybe seems like quite high, but maybe not sufficiently high for you to declare elimination on a national scale. Obviously, you want to be quite certain of that before you declare it. So taking this beyond 2016, so after those last 4 positive cases were observed, we can see that in terms of the sensitivity estimates in the top, environmental surveillance was expanded substantially. And so its sort of coverage in terms of the population on a national level was quite substantially increased. While at the same time, the sensitivity of AFP surveillance slightly declined because primarily because of the adequacy of stool collection sort of declined a little bit. And we can see how that influences then the inferred trajectory of freedom from infection during the 4 years between those last 4 cases and ultimately the official declaration, which was in mid-2020. So we achieve for the combined system, so the points in black, a probability of greater than 95% after around 3 years and approaching 99% by the time that official elimination was declared. So there's a couple of elements that are sort of still require a bit more consideration. In particular, pointing out that in this case, in the sort of re-emergence of wild poliovirus in the Northeast was sort of retrospectively attributed to conflict and inaccessibility in that area at the time. But this sort of disruption was not actually evident in the indicators of surveillance performance that we were looking at, and so actually doesn't factor into our estimated sensitivity of surveillance, which is a kind of, a whole sort of separate rabbit hole to try and go down and understand what the sort of reasons behind that might be. And then secondly, the fact that population catchment of environmental surveillance in the way we've sort of formulated it here is only defined within the LGA boundaries, so within the LGA where the sampling site is. And so we lose some of that coverage that leaks over into neighbouring LGAs. And the extent of the catchment is likely to vary quite substantially depending on the type of site, stuff like recent weather conditions and the particular location and the sort of nature of the population around that site, if it's rural or urban, for example. And so that's a sort of additional source of variability that we need to maybe consider incorporating. But overall, it's reassuring that with this sort of retrospective example, we seem to be yielding sensible conclusions that align with what was really observed.